Thank you very much. I will try to compete with the warm-up of the Totenhosen outside and the barbecue smell in the air and so on. And not the least, this mind-blowing set of fantastic things we have heard throughout the day. So I hope I don't disappoint you by showing you something that is actually pretty simple compared to many of the things we have seen here. So I'm from the Technical University of Denmark, and I would like to right away to acknowledge the people who have actually been in the lab and doing the work. Henrik Bødker Lassen, who sits right down here, is the one who has been doing the measurements and things that you are seeing here. And then the other guys, you can see they're colleagues from a company, Capris. I will show you in a moment why we are working together with them. My group at DTU are pretty new to SNOM. We have had a standard SNOM with an FTIR extension on for the last 3 years maybe. And we started out in the visible range because we thought that would be an easy way to get started. NearSpec told us how to get it aligned and stuff like that. And we had some wonderful gold flakes, monocrystalline gold flakes that came about from our good colleagues, Nicolas Dinger, who sits in the audience here, who got them from Bert Hecht, that you can see on the author list here. So we thought they were good examples of getting started, getting a signal, learning how things work. And the first thing that, where's the laser? Is this switch off? Oh, here, good. The first thing that came out of that, you can see the gold flake here, and was basically that at 633 nanometers, so that's just a Heine laser basically, we could map out the surface plasmon polariton modes on the surface. I don't want to discuss this very much, but just to show you this is where we started. We started in the visible range. Then we got into contact with another one of my good colleagues, Ole Bang, that you can see here. Ole Bang is a big guy in supercontinuum, and he had this new supercontinuum source in the near infrared that, in contrast to many other supercontinuum sources, works with a very low noise level. So we tried to use that supercontinuum source together with the FTIR so that we could, again, map the same surface plasmon polaritons, but now we could do it as function of wavelength here, so from 1.3 to 1.7 microns. Worked fine, and that sort of got us started on understanding how the SNOM is working and what is needed of the light sources and things like that. But this is not what I'm going to talk about now. I will be talking about Terahertz-SNOM, because this is really my turf. So what we did was that, like we saw on one of the earlier slides, that if we want to go sub-wavelength, then it's very easy, we just buy stuff. And this is what we did. We got funding actually from the Carlsberg Foundation to buy a Terahertz extension to the SNOM. So you may not know it, but Carlsberg, you know that they sell beer. But a big part of the earnings actually go into a foundation where they hand out money to fundamental research. It's very nice. Good, like synergy. Anyways, this is the Menlo-based system from NearSpec that can be integrated, like you can see here. There's no sample in right now, but you can see the units here and stuff. It covers like from 0.5 to 2 terahertz. And one of the things we started by doing was that, due to reasons that I will tell about in a moment, we started to look at, can we use Terahertz-SNOM, so near-field measurements, to say something about the conductivity of very thin metal films. What we have chosen here is platinum on high resistivity silicon, basically because it was dirt easy doing that. And sort of the scientific reasoning behind this is that we are collaborating with this company, Capris, who is a tool maker for the semiconductor industry, and they are very interested in new methods for contactless characterization of semiconductor wafers, basically. And the characterization of the conductivity of very thin metal films is, of course, as you can imagine, for connectivity and so on, is a quite important thing there. So we had the opportunity, because we worked with these guys, to characterize the samples independently with micro 4-point probing, and that means we have a set of data where we have Terahertz-SNOM data, and we have, you know, a reference value on what is the sheet conductance of these films, and therefore we have a chance of maybe learning more about how to interpret Terahertz-SNOM data. So you see the samples here. This is just a graphical illustration of it. It looks a little bit like some meta surface or something, but that's actually not really the point here. The point is basically that this was a mask that we had lying around, so we just needed some metal surfaces. And then we did scans of small areas with the SNOM here. So you can see there are, this is, some of you will recognize, this is the picture coming from the system where you can see the tip, and then you can see a small square that we have singled out here. This is basically a 100 by 100 micron scan, so it's a huge scan in the SNOM world, but we wanted to, I don't know why we wanted that, but that's what we did. And then we did, for comparison with the Terahertz-SNOM data, we did micro 4-point probe line scans along the small lines that I've indicated in the different panels here. So that's the data that I'm going to talk about. You can see that some of these regions have like rips and dents here, and this is basically not intentional. This is just because we used, the fastest way of making these structures possible. So when we ripped off the mask, then some of the metal stayed on the mask and stuff. I mean, this is really, really simple stuff. But it gave us the opportunity of actually scanning across. Since it's a rip, then it's a relatively sharp edge, so it gave some nice scan features to look at. Just in case you don't know how micro 4-point probing works, we have 4 electrodes that we can put into contact with a conductive surface, and then we pass a voltage or pass a current through, let's say, pin 1 and 4 here, and measure the voltage drop over pin 2 and 3. And then we change configuration. We apply or drive a current between pin 1 and 3 and measure a voltage drop between 2 and 4. And then there's something called Van der Pau theory that relates these two resistances with each other that allows us to extract the sheet resistance, basically, where we have taken out all sort of uncertainties about whether we are in good contact or whether we have whether we have contact potentials and things like that. So that is a completely standard technique. You may have seen it elsewhere. But the cool thing about what we are, or I think is cool because I don't do it myself, is basically that this company, Capris, they have refined this micro 4-point probe technique to make very, very, very small probes. So you can see this is 3 microns here. I think the smallest probe they have a pitch of 1 micron or half a micron or so they can really do micron level probing here in industrial grade machines that looks like this here and cost like 5 million euros or so. That is very nice. So the result of these measurements, that's basically these line scans of the micro 4-point probing I talked about, looks like this. We had films that are 3 nanometers thick of, recall it's platinum, 3 nanometers, 5, 10, and 15 nanometers, and these are the sheet conductances coming out of these 4-point probe measurements. You can see the resolution of these measurements is very high, but you can also see that the sheet conductance is in the range of less than 1 millisiemens up to maybe 50 millisiemens. So it spans like 2 orders of magnitude or so. 2 orders. That's very nice. I'm not gonna bore you with more SNOM theory, but just remind you of something that we have talked about during the day. You know that we have the point dipole model, sort of the thing that kicked off the whole field, refined to the finite dipole model and so on. And in the finite dipole model, we have this expression, we have seen it a couple of times, that, where are we here? The effective polarizability of the system, which is related to the scattered signal that we measure, is given by the near field reflection coefficient beta here, or the electrostatic reflection coefficient. Now here the problem is that we don't have a bulk sample, so we cannot just use the sort of real electrostatic expression for beta. We need to take into account that we have a thin film, and that if we go to the limit of an infinitely thin film, then we have what we would call the near field version of the Tinkham equations, you would call it, where we basically have the near field reflection coefficient as function of the in-plane momentum Q here. The in-plane momentum Q comes from the fact that we have a super small tip, way smaller than wavelength, and that basically means that in order to sort of represent that very small volume in space, then we need very large vectors in K-space, right? So it is the normal consideration that actually, if we want to describe a thin film interacting here in this volume here, then we need to take into account that this value Q here is actually roughly 1 over the apex radius. All right, this can of course be expanded if we want to into having a real thin film that has a finite thickness and so on, but I'm not going to dwell on that right now. Another thing that is worth considering is that the conductivity of metals is not just the Drude model. We know, or the field knows, that if you are on the very small scale with very high, again, in-plane Q values, then you might need to consider that you have a non-local response of that metal. There's a couple of models describing that. I'm not going to bore you with the details of it, but sort of the traditional thing is the Linhart model from the 50s that was modified by our good friend Mermin in 70 or so, and that is sort of the authoritative representation of what is the permittivity of a metal in the non-local regime here. This reduces to the Drude model if the value of the in-plane vector becomes very small. One can also, approximate a little bit, say that if we are in the thermodynamic limit where we have many collisions, so scattering times per oscillation of the field, then we can use the hydrodynamic Drude model. Common to all of those is that you have here frequency, you have here Q, and then the diagram here shows the real part of the conductivity and the imaginary part over here. And there's this like band going up in the space that I'm plotting here that basically comes from that if you exchange a high momentum with your sample, then you change the Fermi level a little bit, and that actually leads to a resonance frequency instead of a DC resonance, and that's the band that runs up here. So if we are at Qs that are relevant to SNOM, that's actually somewhere in the range here, then actually the conductivity spectrum of a metal, according to what is known in the literature about non-locality, is very much different from the Drude model that you see in here. We still really haven't got a grip on whether this is important for Terahertz-SNOM, but it's at least something to think about. So if we use that realistic in-plane momentum, I forgot to put the citation on here, but basically due to the shape of the tip, there's like a distribution of Q values here, that's this dashed line here, that peaks somewhere at, that value here. Then if we calculate the near field reflection coefficient at that Q value, you can see here, this is for the 4 different thicknesses of metals using the DC conductivity we know we have from the 4-point probing. Then you see that very fast, except for the thinnest film, the near field reflection coefficient is 1 independent of the conductance. And you see the sort of the same effect over here. This is the scattering ratio eta, so that is the scattering ratio we measure in the SNOM. So the signal on the metal divided by the signal on the silicon substrate, right? This is what you see here. For conductances higher than the lowest value we have here, basically that value is constant no matter what the conductivity is. And so therefore, there should be no contrast between the metal films, as seemingly this is a rather poor technique for sheet conductance measurements. And the reason why I continue on the slides here is that we don't always think before we act. So we just did the experiment anyway. And what you see here is the Terahertz-SNOM measurements on this. What you see first are the approach curves, where you see that we have, if we base the resolution on the decay of the approach curves, then we have like 20, 30 nanometers resolution or so. And let us just get to some SNOM data. This is just what we call the white, or what the software calls the white light scans, but this is basically parking at the peak of the Terahertz pulse and then just scanning around on the surface here. And you see here the vertical columns here are the different thicknesses, so 3, 5, 10, and 15 nanometers. You cannot really see the numbers here, but basically as we go up here, the signals increase. You can see the noise gets smaller and stuff, so the signal gets larger. And this is the demodulation order, so n equal 2, 3, and 4 here. So this works very fine. This is just, a lot of red and blue. So we want to quantify it a bit. Let me just skip this here. This is not so important. So here I have tried to summarize everything that I have shown you. This is the film thickness axis. Over here, that's the 3 curves here. This is the terahertz scattering ratio, where we have taken like a little square on the reference area and a little square on the metal area. So just divided the signals between those two. And there you can see that the thicker the film is, the larger the scattering ratio gets. So this S2 here is the ratio between the metal and the silicon substrate. So you can see that for increasing metal thickness, so that means increasing sheet conductance, the scattering ratio goes up, and the higher the order is, the higher that contrast gets. And on the other axis, you can see the sheet conductance from the micro 4-point probes that follows like a nonlinear curve here. It's not linear. This is because of the what's called the confinement effect, that you have an extra scattering channel. Once you have very, very thin films that are comparable to the mean free path, then you start to get extra scattering, so the conductivity actually drops even further than you would think. So apparently it looks like, even though theory told us that it's not really possible, then we actually see a contrast between these different thicknesses here. I have another example here. This is line scans of using the Terahertz-SNOM along the lines that I've indicated here, so the same lines as the micro 4-point probing. So you can see again, there's quite a good contrast between the 3 nanometer platinum film and the 15 nanometer platinum film up here. We don't know why yet. This is work in progress. I wanted to take it along anyway, and today have shown me that was probably a good idea, even though it would be cooler to show something that where we know everything about it. But this seems like a great opportunity to talk to people who know something about this topic here. So in conclusion, actually we can differentiate between conductances of different film thicknesses. In this range here, like from a fraction to like 50 millisiemens or so. We are still working on inverting this, so we actually find the sheet conductance as function of the SNOM signal instead of the SNOM signal as function of the conductance. So we really want to do real spectroscopy. Standard theory, at least as far as we have been able to dig out, does not really predict that there should be contrast. So there's also something from a theoretical point of view, or work to do. Possible explanations can be that we somehow use the wrong in-plane momentum distribution. We heard about that AFM tips are not just AFM tips, and especially these big terahertz ones. I can say that we are using these Rocky Mountain tips that are like 80 microns long or so. But we also know from SEM images that they don't all look the same, and maybe they have a shape that may not fit into the finite dipole model, or whatever reason. This is something we are looking into right now. It could also be that we're actually coupling to, that's something I talked to one of you about during the lunch break, I think. Could be that we are actually coupling to plasmonic modes on the metal surface, that actually changes what we see from what we thought we should see. We also saw these from one of the previous talks about, the standing wave patterns under the metal can influence what the signal looks like. So with this, I would like to say thank you very much. I hope I didn't run over time, but I'm ready for any questions if there's time and you have some.